Yeah, very good morning to all. Today we are going to discuss about the nodal analysis as well as mesh analysis in the networks, electrical networks. So this nodal analysis as well as mesh analysis are the techniques which are used to find out the currents in a particular branches of a network and voltages at the particular junctions of a electrical circuit. Okay, so this nodal analysis is based upon the KCL. This nodal analysis is based upon the KCL application. Whereas mesh analysis we are going to discuss in this particular class, that is also a application of the KVL. We know that KCL and KVL. What is KCL? The KCL is the KCL is states that at a particular junction of a network, the algebraic sum of currents is equal to 0. That is, the currents entering at a junction is equal to the currents leaving that junction. In other words, we call it as a nodes. The junctions are also called as a nodes. Okay. So in nodal analysis, we are finding node voltages by solving a set of equations. Okay, and choosing the node voltages is a very crucial part of this particular analysis, because if we choose how many number of nodes, so based on that one the equations will be dependent. That is, if we choose four nodes, then no four equations will come for the application. So basically, these three are the steps involved in the applying nodal analysis. So if you take any particular network, you need to select a one node as a reference node. We also call this node as a datum node. At the datum node or reference node, the voltage is equal to 0. And whatever the other voltages are with reference to this node voltages. Okay, assign voltages to other nodes with respect to the reference node. Now apply KCL at every node except reference node. At reference node, the voltage is 0. We are assuming. So we are not applying KCL at reference node. We are applying KCL at remaining all nodes. Okay, then we will get a set of equations. We need to solve for the node voltages. If node voltages came, automatically we can find the branch currents. Okay, so let us see one or two examples by taking a simple networks in this class. So consider this circuit. This circuit is consisting of two current sources I1 and I2, and there are R1, R2, R3 are the resistors which are connected in the network. And if you find there are three junctions, this one is the first junction, this one is the second junction, and this is the third junction. We are assuming that this third junction voltage is 0. So we call it as a reference node. And we are having remaining two junctions, 1 and 2. So we need to apply KCL at junction 1 and KCL at junction 2. When you apply KCL at junction 1, so assume that the junction 1 voltage is V1 and junction 2 voltage is V2. Now at junction 1, what is the incoming current? I1. I1 is the incoming current. What is the outgoing currents at junction 1? So one current will flow from 1 to 0 and another current will flow from 1 to 2 through R2. Okay, the first current is through R1 and the second current is through R2. So the current through this particular uh, R1 resistance is, the current through this R1 resistance is like this, and the current through R2 resistance is like this. Then this one is given by V1 divided by R1, and this current is given by V1 minus V2 divided by R2. So in this manner we will get first equation. So if you group the V1 terms and V2 terms, we will get one equation, first equation, this one. Clear? Next, we are going to apply the same KCL at the second node. At the second node, if you observe, the current I2 is coming to the junction in this way. This is I2 current is coming in this way. And at R3, the current may get flowing away from the junction 2. And at 2, from 2 to 1, we are assuming that one more current is flowing through the R2. So according to this diagram, this I2 current must equal to the current flowing through R2 as well as R3. So the same thing we will kept on the equation form. Okay, that equation form, if we kept I2 is equal to V2 by R3 and V2 minus V1 by plus V2 minus V1 by R2. Here you may doubt that why this V2 minus V1 came. In the basic assumption of applying a nodal analysis is the voltage at that particular node we are working with is higher than the other nodes. Okay, except this type of incoming currents. Remaining all, we are assuming that if we are taking node 1 at that moment, we are assuming that node 1 voltage is greater than node 2. And similarly, if we are assuming that node 2, then we will take that node 2 voltage is greater than node 1 voltage. That's why we need to take like this. Now in this equation, group the terms of V1 and V2, then you will get one more equation. Now if you took this particular elements in a matrix form, in particular coefficients of V1 and V2 in the two equations. First equation is this one, second equation is this one. If you kept these two equations in matrix form, then you will get this one. Okay, so we will get one matrix. The matrix of current is equal to the matrix of vectors voltage V1 V2 and the matrix of the inverse of the resistances. The inverse of resistance is known as a conductance. So we can get that I is equal to G into V. The conductance is represented by the letter symbol G and its unit is Siemens. Okay, so in general, the inverse of the resistance is the conductance. The conductance is units is Siemens, whereas resistance units is ohms. Voltage units is volts, current units is amperes. So now can we solve for V? V is equal to matrix G inverse into I. Okay, then automatically we will get set of voltages V1 and V2. Then once V1 and V2 are obtained, what is the current flowing through R1? V1 divided by R1. What is the current flowing through R2? V1 minus V2 by R2. The current flow R3 is V2 divided by R3. That's it. This is the case. Clear? Now, a special case is there. Whenever we are having a voltage source between any two nodes, then we cannot apply the nodal analysis directly. We need to assume that, for example, consider this particular circuit. In this circuit, there is a one voltage source connected between node 2 and node 3. Okay. So at node 1, the already one voltage source is there that is acting as a source voltage VA. So at V1, the voltage is VA. At V2, we don't know the voltage. At V3 also we don't know. But V2 difference V3 is equal to VB. That we know. We know. So this type of arrangement, whenever we occur, we call that as a supernode. The combination of 2 and 3 will form a supernode. So whenever these supernodes are coming in the picture, then we need to apply the KCL for supernode in combination. That is, so we will apply KCL combinedly for the node 2 and node 3. So how to apply? V2 minus V1 plus V2 divide V2 minus V1 by R1. See, just I will annotate. See, V2 minus V1 is divided by R1 current will be like this. And V2 divided by R2 will be like this. At the same time, you need to take the currents flowing through the currents through that junction 3 also. V3 divided by R3 will become the current in this fashion. Now that will be equal to 0. Okay. So that we will formulate in the next slide. See, V2 minus V1 by R1, because at the node A, that is first node, the current is equal to VA. Okay. So V2 minus V1 by R1 plus V2 by R2 plus V3 by R3 is equal to 0. So VA is already a known quantity. So automatically V1, V2, V3, you will get one equation. So V1 is known, that is VA. So V2 and V3 will be one particular, you will get one equation like this. Similarly, in this case, V2 minus V3 or V2 difference V3. Similar, in this case, V2 minus V3. Okay, if the polarity is plus here and minus here this side, then V3 minus V2. So whatever V2 difference V3, that is V2 minus V3 is equal to VB. Clear? So we are going to solve 3 and 4, that is equation 3 and equation 4. Then automatically V2 and V3 will get obtained. Okay. So you need to remember is whenever there is a voltage source between two reference non-reference nodes, they form a supernode, and by combining them, we need to apply KCL for the supernode. Clear? We need to apply KCL for the supernode. That is the procedure. Now let us consider this example. In this example, okay, so we are having a reference node 0 and node 1, node 2, node 3. Now you need to, what you need to apply at node 1 voltage, the voltage VA, at node 2 unknown, node 3 unknown, but node 2 minus node 3 voltage is equal to VB. Okay, so whenever you want to apply a super node, how to apply is just, so at node 2, one current will flow through R1, one current will flow through R2, and one current will flow through R4. So V2 minus VA divided by R1. This one is related to this particular current. And V2 by R2 is related to this one. V3 by R3 is related to the this one. The current flowing from node 3 to R3. And V2 minus V3 divided by R4 is the current flowing in this manner. And V3 minus V2 divided by R4 is current flowing like this. These two terms normally, in this case, it will be cancelled. Okay, so you are getting one equation. You are getting one equation. Now at the super node, V2 difference V3, V2 minus V3 is equal to VB. So that is the procedure. Now we will see one example. In this, a question will be given like this. Find Vx using nodal analysis. Where is Vx? This one. This one is the Vx. Vx is the voltage across 9 ohms. Now in this one, so here we are taking how many nodes? Node 1, node 2, okay, and this one, node 3. Out of these three nodes, this one is the reference node. Reference. So we will take this one and this one. Okay. So at node 1, if you apply KCL. So how to apply? Because it is a super node is there. So you can't apply KCL directly. You need to apply KCL combinedly for this node as well as for this node. Now you calculate. So V1 divided by 2. That is the current flowing in this manner. Similarly, V2 divided by 9, that is the current flowing through this one, is equal to 11 amperes is coming this side. So V1 by 2 plus V2 by 9 is equal to 11. Okay. Similarly, what is the supernode equation? V1 difference V2, that is V1 minus V2 is equal to 22 volts. Now, if you solve these two equations, these two are two equations in the V1 and V2. Then if you solve, you will get V2 is equal to 0. Whenever V2 is equal to 0, what is Vx? Vx is the voltage across 9 ohms. So V2 is equal to 0 means, so Vx is also 0. So you just check, cross check. You will get answer. Clear? Next. Similarly, mesh analysis. So mesh analysis is, it is another way of analyzing circuits. In this mesh analysis, what we are mainly using is we are using KVL to find mesh currents. It is applicable only to planar circuits. Whatever the mesh analysis, nodal analysis is okay. Nodal analysis may be applicable for anything, but mesh analysis is applicable for only to a planar circuit. Planar circuit means if we spread all the elements, then all the nodes must be in one plane. That is known as a planar circuit. Okay, mesh analysis uses the following steps. Assign mesh currents to the all meshes. Mesh means loop. Mesh meaning is loop analysis, loop. Apply KVL to each of the loop. Then solve the resultant simultaneous equations for currents. In this mesh analysis, what you are getting is you are getting loop currents. Whereas in the nodal analysis, what you will get is we are getting node voltages. Clear? So now let us see how it will be implemented. Consider circuit with two voltage sources V1 and V2. So here, how many loops are there? Loop 1 and loop 2. We call that mesh 1 and mesh 2. So if we apply KVL for the mesh 1, what is the KVL for mesh 1? So here, according to the KVL, in a loop, in a closed loop, the algebraic sum of voltage is equal to 0. In other words, the source voltage is equal to the voltage drops in a loop. So V1 is the source. So minus V1 plus what is the drop in this R1? If you are assuming I1 as a loop current, I1 R1 is the drop across this particular R1. Whereas if we see R3, if we consider this first loop, the current we are assuming is flowing from up to down in this manner. So whenever we are assuming current flowing from up to down, I1 is in the same direction. I1 is from up to down. Whereas I2 will be in reverse direction. So what is the resultant current flowing in up down direction? I1 minus I2. This is the resultant current flowing in the downward direction, I1 difference I2 into resistance R3 is equal to the voltage drop in this R3, clear, is equal to 0. So you can group whatever the I1 terms and whatever the I2 terms in this equation. Similarly, if we apply the mesh analysis for the second equation, so in the second loop, the voltage source, how the current, loop current is entering? Loop current is entering through the positive terminal of the source. So then we can take it as a plus. The voltage drop we can take. So how many voltage drops? Voltage drop across R2, voltage drop across R3. We are taking the voltage V2 also as a drop because the current, loop current is entering in the plus terminal. So you can take reverse also. If you are taking I2 as a reverse direction, then you need to take V2 as source voltage minus V2. So anything is valid. You can take either in this clockwise direction or anti-clockwise direction. Depending upon how you are taking the directions, your loop equations will vary. Clear? So similarly, apply KVL for mesh 2. If you apply KVL for mesh 2, what is the current through R3? We are assuming the current in the direction of I2 while dealing with the loop 2. So what is the current flowing through R3 from down to up? It is I2 minus I1, okay, into R3. The voltage drop is I2 minus I1 into R3. The voltage drop will be developed in this manner here, in this manner. So what is the voltage drop in the R2? I2 into R2. The voltage, so V2 is also in the same direction. That's why you need to take plus for the three elements. This is. Now you are having a one more equation in terms of I1 and I2. You regroup them. You can regroup them. So if you regrouping, you will get one more equation. If you solve 5 and 6 for the I1 and I2 linear equations, then you will get some values for the current and I1 and I2. So you need to arrange those two equations. You can arrange in the matrix form. Why we are talking about the matrices is, if number of equations are more, then we cannot solve by means of normal algebraic methods. We need to apply the matrices. Especially in the matrices also, we are using Cramer's rule. Clear? So in this way, you need to write and solve. So now we will see one example. A circuit with current source. For example, whenever we are having a one circuit, in that circuit between the two loops, one current source is there. How to do it? Then we can't know what is the current flowing through this current source. In that case, that one is known as a super node. That one is known as a super node, super mesh, sorry, super mesh. Okay, mesh 1 is this one, mesh 2 is this one, but between mesh 1 and mesh 2, you are having one current source. That is called as a super mesh. Okay, whenever this super mesh is there in your circuit, how to apply KVL? We need to apply KVL for entirely commonly to the mesh 1 and mesh 2. Commonly to the mesh 1 and mesh 2. So that is the technique. Whereas in the case of supernode, we are applying KCL for both nodes. But in this case, we are taking the loops. The loop 1 and loop 2 combinedly we are applying KVL. Okay. So now see this, how it will be applied. You can remove this particular branch because you are applying combinedly for the loop 1 and loop 2. In the loop 1 current I1, in loop 2 current is I2. So you combinedly apply the KVL like this. V1 minus V1 is equal to I1 R1 plus I2 R2 plus V2 is equal to 0. Okay. So if you regroup that elements I1 R1 I2 R2, you will get some equation V1 minus V2. Similarly, in case the current source is Ix is directed upwards. So which loop is directed upward? Second loop is directed upward current and first loop is directed downward. So I2 minus I1 is equal to Ix. That is one more equation. Now you are having a similarly two equations, this one and this one. Now if you solve these two equations 7 and 8, you will get loop currents I1 and I2. Once the loop current is known to you, then what is the voltage drop across R1? V1 is R1 voltage drop is I1 into R1. R2 voltage drop is I2 into R2. So like that. R3 voltage drop is, so that based upon the magnitudes of I1 and I2. So I1 difference I2 into R3. That is the voltage drop across R3. Clear? So now we will see one or two examples and wind up this session. So here in this case, you are given a question like this. Find Vx using mesh analysis. Vx is the voltage across this one. In this, what happens? There are two loops. One loop here, one loop here. There are two loops. One loop is here like this and one more loop is like this. So here in between these two loops, one current source is there. This case is super mesh. It will be super mesh. Super mesh. Okay. So whenever the super mesh is there, automatically what happens is you need to apply KVL combinedly for this two loops like this. So whenever you are applying KCL, sorry, KVL. Here, the current voltage drop between across 2 ohms resistor will be developed like this. So I1 into 2 plus what is the voltage 22. 22 is also in the same direction plus 22. 2 I1 into I1 plus 22 plus here current I2 is flowing from up to down. So now 9 I2. So you will get like this one equation. Similarly, here you are assuming this is I1 and this is I2. So what is the I2 difference I1? I2 difference I1 is equal to 11. Okay. But similarly, I1 difference I1 minus I2 is equal to minus 11. If you solve these two equations, then we will get some value, I2 value. So I2 into 9 ohms is equal to the voltage here. Clear? I think you understand this particular concepts. So I am giving you some problems as your classwork. If you are having any clarifications or any doubts with respect to this particular lecture, you can contact me at my email ID. Okay, so you can contact me at either in the classroom or at our either you can directly approach me as chiranjeevi dot triple E gnit at gniindia.org. Okay, you can contact or you can mail your query to this email ID. Thank you. Have a nice day.